Welcome back to The Explainer. Today, we're skipping the basics and jumping straight into the invisible, high-speed world of your computer's operating system. We're talking about the ultimate multitasker, the CPU.
Think about this for a second. How exactly does your machine, maybe even one with just a single-core processor, manage to stream a Spotify playlist, download a massive gigabyte file, and run a resource-heavy web browser all at the exact same time? Honestly, it feels a bit like magic, right? But behind the glass of your screen, there's an absolute masterclass in high-speed juggling going on.
So here's our game plan for this explainer. We'll uncover the invisible CPU juggler, break down processes, threads, and PCBs, and then use a pretty handy bicycle assembly analogy to explain context switching. After that, we'll look at the algorithms making the tough scheduling calls, and wrap up with some real-world applications.
All right, part one, the invisible CPU juggler and how it actually allocates the processor.
Meet the Processor Manager. This system component is essentially the floor boss. It's totally responsible for allocating the processor to execute incoming jobs and managing the tasks of those jobs. Basically, it decides exactly who gets to use the hardware and for how long. Without this manager keeping things fair and efficient in a multi-programming environment, your computer would literally just freeze up trying to do two things at once.
Moving on to part two, processes, threads, and PCBs. Let's understand the workload.
To really grasp how that manager works, we have to define what's actually being managed. The crucial distinction here is between a program and a process. A program is just an inactive unit of work, like a static file sitting quietly on your disk. But the very second you double-click it, boom, it becomes a process. It's now an active entity, a living instance of that program that absolutely demands CPU resources to execute.
And modern systems take this even further with threads. A thread is the absolute smallest unit of execution created by a process. It can be scheduled and executed independently while still sharing resources with its parent. This means a single web browser process can use one thread to fetch images and a totally separate thread to handle your text input. It's a massive game changer for efficiency. Now, keeping track of all these moving parts requires serious organization. The system handles this using control blocks, specifically thread control blocks and process control blocks. Think of them as highly detailed, unique ID cards. They store the exact status, priority level, and memory location of every single thread and process. They tell the operating system exactly what's going on at any given nanosecond.
Okay, part three, the bicycle assembly analogy, diving into interrupts and context switching.
What happens when priorities suddenly shift? Imagine you're the CPU, and your current job is assembling a bicycle step by step. Suddenly, a neighbor injures themselves with a power tool and yells for help. This emergency is the perfect analogy for a hardware interrupt. Obviously, providing first aid is way more critical than finishing the bike right now.
So you do what's called a context switch. Step 1 was building the bike. Step 2, you get the interrupt. Step 3 is the actual context switch, where you literally mark your exact place in the bike manual so you can flawlessly return to it later, and you drop your tools. Step 4, you execute the new job, providing first aid. Once the emergency is totally resolved, you grab your manual and pick right back up on the bike exactly where you left off. No lost progress.
Which brings us to part 4, the CPU scheduling algorithms. Time to make the tough calls.
Here's the core issue, known as the scheduler's dilemma. The system has to constantly trade off maximizing throughput and CPU efficiency against minimizing wait times and ensuring fairness for all jobs. You can't have it all. If you favor one type of task to push maximum data through, you're going to penalize a user who just wants a quick response. It's a continuous, brutal balancing act for system designers.
And there are a few ways to tackle this. You have non-preemptive algorithms like first come, first served, which is super easy to implement but gives you wildly unpredictable turnaround times, or shortest job next, which minimizes wait time but might indefinitely postpone longer jobs. Then you have preemptive options like round robin. That one provides reasonable response times by giving everyone a tiny time slice, but it requires overhead for constant context switching. And earliest deadline first attempts timely completion but needs extra overhead just to monitor shifting deadlines.
That earliest deadline first, or EDF algorithm, is actually pretty incredible for real-time systems. It dynamically adjusts task priorities based on impending deadlines. But there's a hard truth here. It cannot perform miracles under system overload. If you have 18 units of work queued up, but only 15 units of actual time available before the deadlines hit, something is going to fail. The math just won't allow it.
Let's wrap this up with part 5,
Real-world applications and takeaways. Your CPU in action.
So how does this theoretical juggling act actually play out on your laptop? Well, if you open up your task manager, you'll quickly realize that idle time is a complete illusion. Even when you're doing absolutely nothing, your operating system is aggressively utilizing background threads. It's scanning for malware, checking software licenses, downloading updates, all completely behind the scenes. And you don't even notice a stutter, all thanks to that lightning-fast context switching we just talked about.
To distill all this down, here are the core takeaways from today's explainer. First, the processor manager is always actively balancing fairness and speed for a single CPU. Second, remember that programs are just passive files, while processes and threads are the active execution units doing the real work. Third, context switching is the absolute secret sauce that lets the CPU pause tasks, handle high-priority interrupts, and resume flawlessly. And finally, scheduling algorithms are always navigating the tough trade-offs between throughput, fairness, and response time.
I want to leave you with a quote from the philosopher and mathematician Blaise Pascal. He said, "Nature acts by progress. It goes and returns, then advances further, then twice as much backward, then more forward than ever." It's surprisingly fitting for computer science, right? Systems advance by switching, returning, and ultimately pushing our capabilities further than ever before. So next time you've got 20 tabs open while rendering a video, ask yourself, as our everyday demands for extreme multitasking keep growing, what entirely new, invisible tricks will the algorithms of tomorrow need to invent just to keep up?